Okay, Chemistry 1411. This is chapter 21, which deals with nuclear chemistry. This is the last chapter that we do in Chemistry 1411. And this first figure here, I don't have a lot to say about this, except for that it was so beautiful that I decided to include it in the slides. But if you've ever heard of a PET scan, so a PET scan, and all I'm really going to say about a PET scan, which is a positron emission tomography scan, you can see that you can use a PET scan to analyze all kinds of, parts of the human body, and you can read this this text down here that explains what's going on. But the idea is that we're using nuclear chemistry in order to determine, various diseases or different problems that people have, and it's a good way to analyze, the human body without being too invasive. And we're going to talk about later on what a positron is. This is something that we haven't discussed yet in class. It has the same mass as an electron, but it has the opposite charge as an electron. So it's like a positively charged electron. You're like, what? Okay. Anyhow, but we'll discuss that later on. So something to kind of whet your appetite there. Well, this is where I really wanted to start, and that is in a comparison of nuclear and chemical equations, because so far, all through General Chemistry 1 and General Chemistry 2, up to this point, all you have dealt with are chemical reactions. We always started with some elements, and we ended up with the same elements. So no elements were changed. And if you're wondering, can you change an element? The answer is yes. I'll get to that in a second. But everything we looked at involved atoms rearranging by breaking and forming bonds, right? We looked at heats of formation of reactions, for example. We only talked about electrons as being involved in reactions, especially valence electrons, right? We talked about electrons in our reactions. What else? Reactions were accompanied by absorption or the release of small amounts of energy, right? We could have endothermic or exothermic reactions. And we saw that rates of reaction, and this goes back to our kinetics chapter and our equilibria chapter too, but the rates of reaction are affected by temperature, pressure, concentration, catalysts as well. Now, nuclear reactions, that's going to be the focus of chapter 21. What are nuclear reactions about? Well, now we're going to be talking about elements being converted into different elements, right? Something completely foreign to what we've looked at, or not foreign, but completely different from what we've looked at up to this point. Now we're going to start talking about protons and neutrons being involved in our reactions, as well as electrons. And instead of just a little bit of energy being absorbed or released, we're going to talk about huge amounts of energy being absorbed or released. And that's where the whole concept of nuclear power comes from, because nuclei possess a huge amount of energy when they undergo, or certain types of isotopes undergo fission. Anyhow, and then we're going to look at the fact that reaction rates are not affected by things like temperature, pressure, and catalysts. So again, we could put here chapter 21 for nuclear reactions, and we could put all other chapters would fit over on this side right here. So we take, a whole year to talk about everything else, and then we spend a little bit of time talking about nuclear chemistry at the very end of General Chemistry 2. Well, I want to refresh your memory about nuclear symbols. So nuclear chemistry, what is the definition of nuclear chemistry? It's the study of reactions that involve changes in nuclear structure, right? Nuclear structure denotes the nucleus. And so I want to review with you the nuclear symbols. I know that you all know what an atomic symbol is by now, right? B here represents boron. But the number on top, this is our mass number. Sometimes we call this A. So we'll say mass number, which is A. And then down at the bottom, we have our atomic number, which we oftentimes call Z. So we have our X for our element, then we have A, which is our mass number, and Z, which is our atomic number. What's mass number? Mass number is the sum of protons and neutrons. So the sum of protons and neutrons, we could put here neutrons plus protons. And Z is simply the number of protons. And remember that the number of protons is what identifies or determines the identity of an element. And so in nuclear chemistry, we're going to see reactions where we have changes in numbers of protons. When referring to a single type of nucleus, we often use the term nuclide. So again, if we're talking about a boron nucleus that has, of course, 5 protons and 6 Neutrons, we would call that boron 11. So nuclide is a definition you need to know. Protons and neutrons that are found in the nucleus, we call these collectively nucleons. So when you hear me say the word nucleon, I just mean the collection of neutrons and protons, not electrons, just neutrons and protons. Going back to your General Chemistry 1 days, I know that in my 1401 class, I showed a picture of like the Houston Astrodome or something, and then it had a marble in the middle of it or something like that. The whole idea behind that picture in my class last semester was to explain to you that the size of a nucleus is very small compared to the overall size of an atom. Here you see the size is quantified. A nucleus is around 10 to the negative 15 meters, whereas the diameter of an atom is on the order of 10 to the power of negative 10 meters. So the nucleus is much smaller. Put in everyday terms, if you had to explain this to somebody on the street, you'd say, take the biggest football stadium that you know and take one blueberry and put it in the middle. And that blueberry would be the size of the nucleus, roughly, with respect to the size of the atom, which would be represented by the entire football stadium. What else can we say about nuclei? Okay, nuclei are made up of protons and neutrons. They're very small. Well, this is one that it's very difficult to wrap our heads around. I find it's very difficult to understand this, and that is nuclei are extremely dense. And when I say extremely, I mean extremely dense, okay? You think about water, which has a density of 1 gram per mole. You think about the most dense atoms, okay, or the most dense elements that are known to man have densities of around 20 grams per milliliter, so about 20 times the density of water. But then if you look at the density of a nucleus, the density of a nucleus is around 1.8 times 10 to the 14 grams per centimeter cubed, or 1.8 times 10 to the 11 kilograms per centimeter cubed. I'm sorry, you guys, but I can't even understand that. So I try to think about it, but I just even wrote here in my notes, I have difficult to comprehend how something so small could be so heavy. But that is the density of a nucleus. And if you Google that, you can find all kinds of different comparisons. You know, they'll say, oh, if you had, you know, a nucleus the size of the tip of a ballpoint pen, it would weigh, you know, as much as so many Freightliner trucks or something like that. But the whole idea is that a nucleus is very, very tiny and very, very dense. Well, with that in mind, let's start by taking a look at a problem that involves a density calculation. It says a neutron star in a galaxy that's far away has a mass that's equal to 2.4 solar masses. It tells us what one solar mass is. 1.99 times 10 to the power of 30 kilograms. Is it just me or is that heavy? Yeah, that's pretty heavy. Anyhow, and it has a diameter of 26 kilometers. What's the density of the neutron star? And they tell us that we want to calculate it in kilograms per meter cubed. So I'm going to convert this. My diameter is equal to 26,000 meters, since I want meters. And everybody should know that radius is equal to diameter over 2. So if I want the radius, I take 26,000 meters, I divide it by 2, and I get 13,000 meters as being the radius. The reason that I need the radius is because if I want to use the formula, density is equal to mass over volume, since the neutron star is a sphere, okay, its volume is going to be equal to 4/3 times pi times r cubed. So we can put that in our denominator, and our mass is going to be equal to what? 2.4 times the solar mass. So we have our mass as being 2.4 times 1.99 times 10 to the power of 30 kilograms. That's our mass of our neutron star, divided by the volume, which is 4/3 times pi times r cubed, which is 13,000, I'll just say 13 times 10 to the 3 meters. And I cube all of that. Now I've shortened this or simplified it to 4.78 times 10 to the power of 30 kilograms divided by 9.20 times 10 to the power of 12 meters cubed. And we get the density of a neutron star, which is a sphere, is equal to 5.2 times 10 to the power of 17 kilograms per meter cubed. Okay, kilograms per meter cubed. Now, is it just me, Jerry, or is that very dense? That's extremely dense, right? We saw that the density of a nucleus was around what? 1.8 times 10 to the power of 11 kilograms per meter cubed. Well, what we're going to do in the second part here is we're going to compare the density of a neutron star to the density of a uranium nucleus. So uranium is element number 92. If you look at your periodic table, it's found way down in the lanthanides. So we have uranium, and it says here how much, or how does the neutron star's density compared to the density of a uranium nucleus, which has a diameter of about 15 femtometers, and it tells you how much a femtometer is. Well, let's do it here. First of all, I know that in one atomic mass unit, I have 1.66 times 10 to the negative 27 kilograms. That's something that we went over in General Chemistry 1. So I'm not going to go over that again right now, but we have density is equal to mass over volume. We know that the mass of our uranium is 235 AMU. I'm just going to use 3 sig figs because we only have 3 here. We only have 2 there. Or sorry, we only have 2 there. Anyhow, where was I? There we go. All right, so we have 235 atomic mass units. Again, one atomic mass unit weighs what? 1.66 times 10 to the negative 27 kilograms. Okay, and again, I went over this in General Chemistry 1. Where do you get one atomic mass unit? I'll just kind of say it to you here. If you have one atomic mass unit, one atomic mass unit is equal to the mass of 1 carbon 12, okay, divided by 12. So it's 1 carbon 12, or 1/12 of a carbon 12, okay? So that's, you take 12 grams, you divide it by Avogadro's number, you divide it by 12 atoms, you end up with 1.66 times 10 to the negative 24 grams, which is 1.66 times 10 to the negative 27 kilograms. Anyhow, so atomic mass units, then we're going to divide that by the volume, which is going to be 4/3 times pi times our radius cubed. So if our diameter is 15 femtometers, so we'll say here diameter is equal to 15 times 10 to the negative 15 meters. That means that radius, you just divide that in 2, so you'd have 7.5 times 10 to the negative 15 meters. There we go. So let's plug that number in. We have 7.5 times 10 to the negative 15 meters. We cube that. I simplified that to density as being equal to 3.90 times 10 to the negative 25 kilograms divided by 1.77 times 10 to the negative 42 meters cubed. And you get the density is equal to 2.2 times 10 to the power of 17 kilograms per meter cubed. Now, if I compare that to the density of the neutron star, so we'll put here my neutron star was what? It was 5.2 times 10 to the power of 17 kilograms per meter cubed. You see that the neutron star is about 2 times more dense than the uranium nucleus. So either way, the take-home message is that they're both extremely dense, and that the density of a nucleus is very high. Okay, very, I would say, difficult to comprehend how something so small could be so dense. Well, what is it that holds the nucleons together in the nucleus? Okay, we have protons and neutrons in our nucleus. What is it that holds them in there, right? Because we know that if protons are positively charged, they're going to repel each other, right? We know that like charges repel. Well, there must be a force that's stronger than the repulsive force between protons that holds the nucleus together, and we call that the strong nuclear force, the force of attraction that holds the nucleus together. Okay, again, since those positive charges are so close to one another, you have to have a really strong force, the strong nuclear force that binds those protons together in that in the nucleus. It says here that the strong nuclear force is much stronger than an electrostatic force. And in fact, It's the strong nuclear force is one of the four fundamental forces, being strong nuclear force, gravitational force, electromagnetic force, and a nuclear weak force that we'll talk about later on. Okay, so that's what holds all those nucleons together in the nucleus. Again, nucleons are protons and neutrons. Again, I'm repeating myself here. Protons are going to repel each other, but the strong nuclear force holds them together. So that must be a tremendous amount of energy that's going to hold those protons together in that nucleus, since they all have like charges. Well, I want to switch, kind of our train of thought here just for a second, and think about how much energy does it take to hold all those protons and neutrons together in that nucleus. And we're going to evaluate that in terms of what's called nuclear binding energy. Let me show you. If you were to take 9 protons and 10 neutrons and combine them to make fluorine-19, not only do you produce fluorine-19, but you're also going to release some energy. Now, before we get into the details of it here, I want to tell you that you see this thing here that says P with a 1 and a 1? That represents a proton. And this thing here, N with a 1 and a 0, that represents a neutron. So those represent a proton and a neutron. I'll write that over here. So 1, P1, this represents a proton. Okay? And then 1 and 0, this represents a neutron. And if you're wondering, where does that come from? Well, the P and the N are obvious. Remember that the number on the top represents the mass number. That's the sum of protons and neutrons. Well, if I have 1 proton, I have 1. And if I have 1 neutron, I have a mass number of 1. But remember that you have the atomic number down here at the bottom. That represents the number of protons. If I have 1 proton, of course, I've got 1. If I've got a neutron, I've got no protons. And so it's 0. So that's where those symbols come from. Now, again, if I combine 9 protons and 10 neutrons, I make a fluorine-19 nucleus. Plus, I'm going to release some nuclear binding energy. How much nuclear binding energy is going to be released? Let me show you. If you tally up the mass of 9 protons, and a proton weighs 1.0073 atomic mass units, and you add it up with 10 neutrons, which weigh 1.0087 AMU, you tally all that up, you get around 19.15708 AMU. Well, what happens is, if you actually measure the mass of fluorine-19 in a mass spectrometer, so this value comes from a mass spectrometer, which gives you a very accurate mass for whatever you're analyzing. You see the actual mass is 18.9984 AMU, which you can see is lower than what we calculated by 0.1587 AMU. So the difference between the calculated mass and the actual measured mass on the mass spectrometer, we call that the mass defect. This here is called a mass defect. Now, if you're like, question mark, where did the mass go? How can you destroy mass? Well, hold on. It says here, follow along with me. I know there's a lot of text here, but follow along. It says, the loss in that mass, that little bit of mass, that mass defect, accompanying the formation of an atom from protons and neutrons and electrons, of course, is due to the conversion of that mass is going to be converted into energy. Okay? And that energy is called the nuclear binding energy. It's the energy that's produced when the atoms, nucleons, are put together in that nucleus. It's also the amount of energy that's required to break the nucleus into its protons and neutrons. And that brings us to the mass energy equivalence equation, which you all know was put forth by Einstein, equals mc squared. Well, before we do that, I just want to show you one more thing, okay? It says that the nuclear binding energy is also the energy needed to break a nucleus into its constituent protons and neutrons. So if I take this reaction up here and I write out the reverse of it, if I wanted to take fluorine-19, and I know there's not a lot of room here, but if I wanted to take fluorine-19 and break it apart into its 9 protons plus 10 neutrons, 10 neutrons, in order for me to do that, I would have to put in nuclear binding energy. So I'd have to put in the same amount of energy. So how do we calculate how much energy is required? Now, I know you've all seen the form of this equation on t-shirts and posters. E equals mc squared, which is the mass energy equivalence equation. It relates what? Mass and energy to each other. So energy is equal to mass multiplied by the speed of light squared. Well, I write it like this. The difference in energy is going to be equal to the difference in mass, so the mass defect, that's what I mean by the delta M. So the delta M is the mass defect multiplied by the speed of light squared, okay? And that delta E tells us how much energy is going to be released. Well, let's analyze it using our mass defect. So the mass defect that we calculated on the last slide was negative 0.1587 AMU. If we multiply that by the speed of light squared, we end up with this number right here. Negative 1.43 times 10 to the power of 16 atomic mass units times meter squared times second squared. Well, we can use these conversion factors in order to convert these units into joules. How would I do that? Look, I have negative 1.43 times 10 to the power of 16 atomic mass units times meter squared divided by second squared. Okay, I know that doesn't look like a square. There we go. Okay, I have in 1 kilogram, I have 6.022 times 10 to the power of 26 AMU. And I know that in 1 joule, I have 1 kilogram per meter squared divided by seconds squared, like that. Look at what cancels. My kilograms cancel, my meter squared cancel, my second squared cancel, my AMU cancels, and I'm left over with only joules. And so I get that my delta E is equal to the negative 2.37 times 10 to the negative 11 joules that you see down here at the bottom. Now you might be thinking, come on, Mr. Dion, 2.37 times 10 to the negative 11. First of all, why is the number negative? Well, I wrote down the mass defect as being a negative number. And what that tells me is that when I bring those nuclei together, the reason the nuclear binding energy, the delta E, is negative because energy is released, right, into the atmosphere. Okay, so energy is being released, and that is why I have a negative number. So energy is released. Well, again, as I was saying, it doesn't seem like a very big amount of energy, does it? 2.37 times 10 to the negative 11 joules. You're like, come on, Mr. Dion, we looked at reactions that were like exothermic to the tune of 100, kilojoules per mole. That doesn't look that much. Well, hold on. Those were kilojoules per mole. This is for 1 fluorine nucleus. What if we look at it in terms of the number of moles? So we take that value and we multiply it by the fact that we have Avogadro's number of nuclei in 1 mole. Then we get 1.43 times 10 to the power of 13 joules, or look at this, holy moly, negative 1.43 times 10 to the power of 10 kilojoules per mole. Now we're looking at, amounts of energy that are way bigger than any exothermic reaction that we looked at in, the thermochemistry chapter of General Chemistry 1. So that tells me that since 1.43 times 10 to the power of 10 kilojoules are released for every mole, that means the nuclear binding energy, or the amount of energy that it would take to break apart the nuclei, right, is the same amount. But now it's a positive number because it'd have to put that energy in. Well, if we're comparing a bunch of different nuclei, what might be a little handier is to evaluate the nuclear binding energy per nucleon, right, per the number of protons and neutrons collectively that we have in a nucleus. So since in my fluorine nucleus, I have 9 protons and I have 10 neutrons, I tally those up, I get 19 nucleons. I divide that and I get 1.25 times 10 to the negative 12 joules per nucleon. Now, another way to write this unit out instead of joules per nucleon is mega electron volts per nucleon. And that is used pretty often in our textbook. So I'll show you how to do that conversion factor right here. We use the conversion factor that 1 electron volt is equal to 1.602 times 10 to the power of negative 19 joules. So if I have my 1.25 times 10 to the negative 12 joules per nucleon, and I have 1 electron volt for every 1.60 times 1.602 times 10 to the negative 19 joules. I see that joules cancel, and I end up with a number that is going to be equal to 7.80 times 10 to the power of 6 electron volts. And in 1 mega electron volt, I have 10 to the power of 6 electron volts. And so I end up with 7.80 mega electron volts. So this is a form that's used a lot, is the number of electron volts, which is, again, an amount of energy that it would require to break apart a nucleus. So electron volts or mega electron volts is used quite a bit in our textbook. And I know that many of you are avid readers of the textbook. Well, what if we compare the nuclear binding energy per nucleon and we compare the nuclear binding energy per nucleon versus mass number, right? What's mass number? The total of the number of protons and neutrons. Okay, well, everything doesn't fit on here, does it? Again, mass number, which is A, which is equal to the number of protons plus neutrons. Now look, if you look at the binding energy, when we go from really small atoms, okay, they have small mass numbers over here on the far left. You see that as the mass number increases, the nuclear binding energy increases until I get to a maximum around here somewhere. Now, the maximum is somewhere around iron 56, I think is probably one of the most stable nuclei. Okay, so the nuclear binding energy increases as we go from small atoms all the way up to around iron 56, which is where we hit a maximum. And then as the nuclei get bigger and bigger and bigger, then their nuclear stability starts to drop. And so if you're wondering, what do these things here mean by, fusion and fission? Well, what those mean is that when I'm dealing with fusion, fusion means that I'm bringing nuclei together to make a new nucleus. Okay, so fusion is the combination of two nuclei to make a new nucleus. So if you see that it says here fusion with an arrow going up like this, what does that mean? That means that lighter nuclei are going to have a tendency to combine to make more stable nuclei, right? Why do I see fission over here? Because fission is breaking nuclei apart, right? Breaking a nucleus apart. Now, fission is a lot more common because that's how we get energy for, nuclear reactors. Fusion is a lot more difficult. And, maybe if we have time, we'll talk about fusion a little more later on. But anyhow, fission, what it's saying here is that if you have a heavier nucleus, right, it wants to be more stable, right? It wants to have a higher binding energy. So what are those nuclei going to do? Heavier nuclei are going to break apart in order to become more stable, right? So we see that, again, the whole idea is that as nuclear binding energy per nucleon increases, nuclear stability is going to increase. And so what will any nucleus try to do? It's going to try to move in whatever way it can to become more stable, okay? And if we have a heavy nucleus, it's going to break apart, it's going to undergo fission. And if we have lighter nuclei, they're going to combine or undergo what's called fusion. Now, what did we see in our example over here is that we said a fluorine nucleus had a binding energy of about 7.80 mega electron volts. Well, I don't know if I can see it on here. So fluorine would be around 19. So it's probably, maybe this one. I guess I should use a different color. It's probably like this guy right here, maybe. That might be my fluorine. My fluorine 19, which has a binding energy, nuclear binding energy, equal to 7.80 mega electron volts. And remember that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules, like that. Okay, well, with all that in mind, let's try a practice problem here. And this is example 21.2 from our textbook. It says, determine the binding energy for a helium-4 nuclide in joules per mole of nuclei and joules per nucleus. The mass defect for helium is 0.0305 AMU. Well, we know from General Chemistry 1 that we have an equivalence between atomic mass units and the number of grams per mole. If you have one atomic mass unit, that means the same thing as 1 gram per mole. And so for A, we're starting it with 0.0305 grams per mole. We'll call it that. And we need our mass of our mole of nuclei in kilograms. So to convert that into kilograms, come on, get out of the way. We have in 1,000 grams, we have 1 kilogram. So grams are going to cancel like that. And we end up with the mass of our mole of nuclei as being 3.05 times 10 to the negative 5 kilograms per mole, right? This is the mass of 1 mole of He4 nuclei. Okay, we have the mass. Now, in order for us to determine the nuclear binding energy, we're going to use the formula E is equal to mc squared. And again, I called it the delta E, which is the amount of energy that we're going to get for our nuclear binding energy is going to be equal to delta M, which again, I told you is the mass defect, okay, which we already calculated, right? So there we go, multiplied by c squared. Okay, so let's put some numbers to it. We have our energy is going to be equal to our mass defect, which is 3.05 times 10 to the negative 5 kilograms per mole multiplied by c squared. C is the speed of light, 3.00 times 10 to the power of 8 meters per second squared. So when you punch all that spinach into your calculator, you get that your energy is equal to 2.74 times 10 to the power of 12 kilograms meter squared divided by second squared times mole. Well, we know that a kilogram times meter squared per second squared is equal to a joule. So now we can say that our energy is equal to, is equal to 2.74 times 10 to the power of 12 joules per mole. Now you could work that out into kilojoules, and in the book they work it out into terajoules. That's neither here nor there for me, but the whole idea is this, is that the nuclear binding energy is 2.74 times 10 to the power of 12 joules for 1 mole of He4 nuclei, which only weighs 0.0305 grams, which is about, you know, it's not about, it's for 30.5 milligrams. How big is 30.5 milligrams? You can see it with the naked eye. It's around the size of a drop of water is what it says in our textbook. So just for that tiny little bit of helium, this is what we have for a nuclear binding energy, which is just crazy. You know, that's a huge amount of energy for a small, tiny mass defect, okay? So that's the takeaway message here. We have a small mass defect and we have a huge amount of energy. Well, it asks us to determine it in the number of joules per mole. Now we're going to figure it out in terms of the number of joules per nucleus. So if we know that our energy is equal to 2.74 times 10 to the power of 12 joules per 1 mole of nuclei, and we know that in 1 mole of nuclei, we have 6.02 times 10 to the power of 23 nuclei, like that. Moles cancel out, and we're left over with our energy, which is 4.55 times 10 to the negative 12 joules, like that. That's per mole of nucleus, or for 1 nucleus, excuse me. So that's joules per nucleus, okay? And then it asks us to calculate that in terms of electron volts. So that's just a quick conversion. We have 4.5 E is equal to 4.55 times 10 to the negative 12 joules per nucleus, okay? Multiplied by 1 electron volt has 1.602 times 10 to the negative 19 joules. And we end up with our joules canceling, and we end up with what? It's 2.84 times 10 to the power of 7 electron volts. Right, remember that in 1 mega electron volt, you have 10 to the power of 6 electron volts. So this is the same thing as 28.4 mega electron volts. Like that. There we go. So there's our nuclear binding energy for the helium-4 nuclide when we were given the mass defect. So all we had to use was E equals mc squared. After that, we calculated it per the number of joules per mole in part A, then joules per nucleus in B, and then we just converted it into mega electron volts per nucleus for part C. All right, well, let's talk about nuclear structure and stability. Right, you guys, you know that we have, for most atoms, we have more than one type of nuclide, don't we? Okay. If you have carbon, for example, we can have carbon 14, carbon 14, carbon 12. So out of all the different nuclides, and if you ever do a Google search on radioactive isotopes, I mean, you can find out how many nuclides, some of these elements have, which is, quite a large number. Only about 250 or 260 nuclides are actually stable. So out of thousands, so think about that for a second. We have thousands of different combinations of protons and neutrons to make all these different nuclides, but there's only about 250 of them that are going to be stable, that are just going to exist the way they are and aren't going to either break apart. They aren't going to break apart in some way. If we do a plot of the number of neutrons, so we have number of neutrons on our, where is it? Number of neutrons on our y-axis versus the number of protons on our x-axis, we see that the stable isotopes fall into this narrow band called the belt of stability. Okay, and sometimes it's called the band of stability, a region of stability. Anyhow, that's neither here nor there. But any nuclei that lie to the left or the right to the belt of stability are going to be radioactive. All right, what does that mean? That means they're going to break apart in some way to form a more stable nucleus. Okay, so the nuclide is going to be unstable. So if we look at the band of stability closer, you see all these red dots? These represent stable nuclei. Outside, where it's like fuzzy pink here, that represents other nuclei that are radioactive. Okay, they're unstable nuclei. So if you look at the ratio of protons to neutrons, and if you draw a line that for the number of neutrons and protons being a ratio of 1 to 1, so you see this line right here, we see that the band of stability curves up from that line. What does that tell you? That tells you that when you have really small atoms, right, that have lighter nuclei, the ratio of neutrons to protons can be 1 to 1. But as the nuclei get heavier and heavier, what happens is that the number of neutrons starts to exceed the number of protons. Say, for example, you have a nitrogen-14 nucleus. So what color could I use here? Let's say you have a nitrogen-14 nucleus. Well, nitrogen is element number 7, and so the ratio of neutrons to protons is 7 over 7, which is going to be 1, right? Where did you get 1, Mr. Dion? Look, if you have a mass number of 14, that means you have 7 protons and 7 neutrons, right? Because you've got 7 protons. If we were to do the same thing with iron 56, so let's say we took iron 56, iron is element number 26, the ratio of neutrons to protons here is going to be equal to 1.15. And if we try the same thing with an even heavier atom or nuclide, like lead 207, for example, lead is element number 82, then the ratio of neutrons to protons is even higher. It's 1.52. So it increases. So larger nuclei, the reason why this occurs, why the ratio of neutrons to protons increases as the nuclei get bigger, is because larger nuclei have more proton-proton repulsions and require more neutrons to overcome the repulsions and hold the nucleus together. So we could put here, let's see, ratio of N over P increases as more neutrons are required to overcome the proton-proton repulsions, to overcome proton-proton repulsions. There we go. All right. Like that. Okay. And later on, I don't know if we'll have time to do it today, but later on, we're really going to get into the nitty-gritty of the band of stability. And we're going to say, well, what if you have a nuclide that lies on the low side of the band of stability versus a nuclide that lies on the high side of the band of stability? What are those nuclides going to do to become stabilized, right? And they're going to do different things depending on whether the nuclide is too, or if the ratio of neutrons to protons is too large or too small. But in order for us to really analyze that, we have to get into section 21.2, and we're not there yet. All right, just another point about the band of stability, and this is the figure that you see in your textbook, in the OpenStax textbook. It says here that if you look at isotopes of elements with an atomic number greater than 83, so 83 would be around where? It would be around here somewhere, okay? If you have an isotope that's heavier than 83, what do you see? Is that they're all unstable. Okay, they're all going to be radioactive. So that's kind of interesting. And that's going to be of consequence to us later on. Well, if we take a look at the numbers of protons and neutrons in a nucleus, it says here that certain numbers that we call magic numbers, I'm not kidding, that's what they're called, magic numbers of protons or neutrons produce nuclides that are extra stable. Say, for example, if you have 2, 8, 20, 50, 82, and 126, and you don't have to memorize these numbers, but if you have either of these numbers of protons or neutrons in your nucleus, then it imparts some stability to the nucleus. Here I tried to relate it to the number of valence electrons in the noble gases. So it's kind of like that, but it's like it, but it's different. But it's the same concept that we use. You know, certain numbers have certain inherent stabilities in chemistry class, right? Anyhow, another one, it says that nuclei with even numbers of both protons and neutrons are generally going to be more stable than those that have odd numbers of neutrons and protons. I have this in a table that I'll show you in a couple seconds. And there's another one in here that I didn't include, and that is numbers that are double magic. Let's say you have a nucleus like helium-4, or what are the other ones that they had listed? Oxygen-16, or calcium-40, or lead. Sorry, move it over. If you have lead, lead-208. Okay. Well, if you look at all of these nuclei, everything's a magic number, right? I'm not going to calculate all of them, but you see the number of protons in helium-4 is 2. The number of neutrons is 2, right? 2 is a magic number. If you look at oxygen-16, the number of protons is 8. The number of neutrons is also 8. Here it's 20 and 20. If you look at lead, you have 82 protons and you have 126 neutrons. So those are double magic, and those are really stable isotopes. Anyhow, all isotopes of elements with atomic numbers higher than 83 are radioactive. I went over that on the last slide. And all isotopes of technetium and promethium are radioactive. There are no exceptions to those. Every isotope of those elements are radioactive. All right. Here's that table that I promised you, where you look at the number of stable isotopes and compare it to the number of protons and neutrons. So again, I told you that when you have even numbers of protons and neutrons, they're generally going to be more stable isotopes than when you have odd numbers of protons and neutrons. If you tally this up, you get a total of 265 different stable isotopes. And you can see that when you have everything being odd, the number of protons and the number of neutrons, there's not very many stable isotopes with that kind of configuration. All right, well, that covers the section on nuclear stability and nuclear structure. Let's move on to section 21.2, which deals with nuclear equations. This is a much shorter section. but you need to be aware of the types of common entities. I was going to say particles, but they're not all particles. The types of common entities that are involved in nuclear reactions. Those are protons, which you know about already, neutrons, which you know about already, right? I even showed you the symbol of a proton this morning. I showed you the symbol of a neutron this morning. So nothing new there, protons and neutrons. But now we're going to take a look at what are called alpha particles, beta particles, positrons, and gamma rays. These are all new to you. So I'll go over the representation of all of these entities first, and then we'll get into some practice of balancing equations where we use these entities. So the first one is an alpha particle. If you go back to Rutherford's gold foil experiment in General Chemistry 1, where Rutherford discovered the nucleus and that the atom was mostly empty space, right? And the protons and neutrons were concentrated in the center of the atom. You remember that he fired alpha particles at the gold foil. And I told you that an alpha particle was nothing more than a helium nucleus, right? It consists of 2 protons and 2 neutrons. That, my friend, is an alpha particle. The way you can represent an alpha particle is you can use the symbol alpha. It's got a mass number of 4 for 2 protons plus 2 neutrons, and it's got 2 protons in its nucleus, so therefore it has an atomic number of 2. Or you can use the symbol He to represent it as well, and 4 and 2 in the same way. And so this is a high energy helium nucleus. So again, an alpha particle is nothing more than a helium nucleus. What's a beta particle? A beta particle is really nothing more than an electron. It's just a high energy electron. The way that we represent a fast moving or a high energy electron is you can actually use the Greek letter beta, or you can use the symbol E like this. They have no mass. Now I know that an electron has a mass, but the mass is so small that we can negate it. But what would be, or the charge of an electron is -1. And so we say that they have an atomic number of -1. So we use -1 again for the atomic number. A positron, I'm not going to go into great detail about what a positron is. The book talks about it a little more, and I'm sure there's always one person in the class who's obsessed with antimatter and, science fiction and that kind of stuff. And antimatter isn't science fiction, but a positron is kind of difficult to understand. It's like an electron, but it's got a positive charge. You can just think of it as being a particle that has the same mass as an electron. However, it has a positive charge. Okay, that's what it is. And again, if you want to learn more about antimatter, feel free to read about that in the textbook or research it a little more. The way that we represent a positron is just like a beta particle, except down here we have a +1 because it's got a charge of +1 instead of -1. Again, it's got such a small mass that we negate the mass and we just put 0 up here. A proton, I went over that this morning. You already know what a proton is. It's the nucleus of a hydrogen atom. A proton can either be represented by the letter P. Sometimes we just use a hydrogen to represent the proton. It's got a mass number of 1. It's got an atomic number of 1. A neutron has no atomic number because it's got no protons, but it has a mass number of 1. We use the little n to represent neutron. A proton has pretty close to the same mass as, a neutron has pretty close to the same mass as a proton, but it's got no charge. And the reason why we have to use the word entity and we can't use the word particle is because the last entity is not a particle, and that is a gamma ray. And you remember when we talked about the electromagnetic spectrum, we talked about radio waves, infrared, UV, visible, right? And then we went into X-rays and then gamma rays, which we said were the highest energy form of electromagnetic radiation. Very small wavelength, very high frequency, and therefore very high energy. And these are not particles. Now, gamma rays are usually emitted when you take an element that's in an excited state and then it relaxes back down to a more stable state. From there, it can emit a gamma ray. Well, how would we use any of these entities in a balanced nuclear equation? In order for us to use any of these entities in a balanced nuclear equation, we have to cover a couple of rules. And I promise that this is not difficult. You know, it's very rare that I say not difficult in chemistry class, but if you can add and subtract, you, my friend, can balance nuclear equations. What you have to keep in mind is that you want to conserve mass number, right? Mass number is A. So if we write it our element X, we have A as the mass number and Z as the atomic number. So that means the sum of protons and neutrons in the products has to be equal to the sum of the protons and the neutrons in the reactants. Look at this complicated reaction here. You take uranium-235, you combine it with one neutron, and you get cesium-138, rubidium-96, and 2 neutrons. Holy cow. Wow, that looks really complicated. Well, look, let's tally up the total of the mass numbers that are on here. 235 plus 1. That gives us 236. Okay, over here we have 236. So that means that the sum of all the mass numbers of all my products, 138 plus 96 plus 2 times 1, the 2 is a coefficient, and we have 2 neutrons. So 138 plus 96 plus 2. Put it in your calculator. Take 138 plus 98, and you end up with 236. And so we have to conserve the mass number. The same thing applies for the atomic number, or what we sometimes call the nuclear charge. Same reaction again, uranium-235 plus a neutron gives us cesium-138, rubidium-96 plus 2 neutrons. Look at the total of the atomic numbers. Here we have 92 plus 0, that gives us 92. Here we have 55, 37, and 2 times 0. So 55 plus 37, which gives you 92. So if you're wondering, is that all I've got to do to balance a nuclear equation? The answer is absolutely, my friend. That's all you've got to be able to do. Well, with that in mind, let me find where I was in my slides, which was right around here. And let's try balancing a nuclear equation. We have polonium-212, and it's undergoing some kind of decay to produce lead-208 plus X. So what's X? Well, we have X, and what is our mass number going to be? Here we have 212, and here we have 208. So 208 plus something is going to give us 212. The answer is 4. Right? It's not going to be 2 because we have 208 plus 4 gives us 212. So there we go. We have our mass number and our atomic number. We have 84 over here. Okay, and we have 82 over here. What plus 82 is going to give me 84? And the answer is 2. Well, what has 2 protons? An alpha particle. All right, so I can either call this Hg like this, or I could call it an alpha particle 4 and 2 like this. Either one is perfectly acceptable. Okay, so that's the answer to the first one. If we take a look at the next one, I'm going to give you a second to try to solve the next one on your own. Take a second, and if anybody can tell me what we have as X in the second one, just let me know. Yeah, exactly. And the next one we have a beta particle, right? Because if you take 137, over here we have 137, so that means my X has to have a 0 on top. Here you have 55, and over here you have 56. 56 plus what gives you 55? The what must be equal to -1, so this is a -1. That means that this is a beta particle, right? And you could write it like this as well. Either way works, but this is a beta particle. Okay, does that make some sense to everybody? I hope so. Give me a thumbs up if that makes some sense to you, balancing a nuclear equation. All right, good. Well, with that in mind, make sure you try this question. Okay, this is question 13 from OpenStax. Of course, you have the answer to this or the solution to this in the solutions manual. I'm not going to go over this one right now since we only have 2 hours left in class, but I'm going to let you try this one in your own time, and I want to talk a little bit more about radioactive decay with you. So we're going to move on. You know what? Let's try one. Yeah, let's try one. What time is it? Yeah. Let's try one just for fun. I can't help myself. Can anybody solve for the missing isotope where it has the question mark? I'll just give you guys a second if anybody can solve for this. Does anybody have an idea what is in the question mark that I have in the red circle? Yes, thanks, Jamil. It's phosphorus 30. How did he figure that out? Because you have 27 plus 4, that gives you 31. Over here you have 1. What plus 1 gives you 31? The answer is 30. Okay. Then we have 13 plus 2, which gives us 15. Over here we have 0. What plus 0 gives you 15? The answer is 15. Go to the periodic table. What element is number 15? Let's see, we got aluminum, phosphorus. So it's phosphorus 30. So this is the answer to this one here. It is phosphorus 30. Not sure who that was. Can you guys still see my screen? Sorry about that. Can you still see my screen with question 13 on it? Okay, good. Let's try one more just for fun. Let's try, I don't know, let's try the last one. Let's go all the way to the bottom and try the D. Same thing here. We have 235. Here we have 135 plus 4. So 135 plus 4 is 139. If you take 235 and you subtract 139, you get 96. Okay, so that's going to be your mass number. Here you have 92. Over here you have 55 and 0. So what plus 55 gives you 92? 92 subtract 55 is 37. Go over to the periodic table. Look up element 37. It is rubidium. So it's going to be rubidium 96. Okay, and that is how you balance a nuclear equation. Something everybody can do. Okay, something that everybody can do. Students usually nail these questions. Okay, it's very rare that I ask a question about balancing nuclear equations and people botch them. They're usually pretty well done by my students. Okay, well, let's move on from there and let's talk about what's called radioactive decay. And in fact, you heard the word decay sneak out of my mouth earlier on in the lecture. I mentioned it a couple times. And what radioactive decay means is nothing more than the change of an unstable nucleus or nuclide into a more stable nuclide. That's what we call radioactive decay. So put another way, you could say a nuclide is going to do whatever it's got to do to become more stable. That unstable nuclide that we're starting out with, we call that the parent nuclide. And after the decay occurs, we're left over with a product, which we call the daughter nuclide. Here's an example of a radioactive decay. We have uranium-238. If I write this out, I have uranium-238. Uranium is element number 92. It's going to undergo a radioactive decay to form thorium-234. So thorium-234 is TH234, and thorium is element 90. And of course, I'm going to liberate that alpha particle, and I can just write that like this, my alpha particle like this. So that shows my, my balanced nuclear equation, right? Here I have the parent. No, I guess it's already written there. I have the parent. Here I have, let me write it here. I have the parent. I have the daughter, and this is the particle or the entity that was liberated during the decay, which was an alpha decay in this case. So a radioactive decay, we have a parent and we end up with a daughter. Well, this is just a figure that comes from your textbook. It's not of great consequence to us because by now I'm pretty sure you get the idea that a beta particle is negatively charged. Right, and if it's negatively charged, it's going to be attracted to the positive pole of a magnet. Alpha particles are positively charged; they would be attracted to the negative pole of a magnet. Right, a beta particle is a lot lighter than an alpha particle, so it's going to be deflected a lot more than an alpha particle would. And then a gamma ray has no charge, and therefore it's not going to be deflected at all. Well, let's talk about the types of radioactive decay that we could have. We just looked at the decay of uranium to thorium, and now and that was the result of an alpha decay. But I want to take a look at different types of radioactive decay. So see if you can follow along with me here. I know we're in the last few minutes of the lecture, but I want you to pay close attention here. The first one is a beta decay. right? In beta decay, what are we going to liberate? We're going to liberate a beta particle. You see two examples here. Now, what's happening overall? We're starting out here with carbon 14, and we're ending up with nitrogen 14, right? So we're changing an atom into another atom. We're going from a carbon to a nitrogen. So what's happening here is that we're decreasing the number of neutrons by 1, right? Because the beta particle has a atomic number of -1. So in order to balance that, our daughter has to have an increase in the number of neutrons, sorry, an increase in the number of protons by 1, a decrease in the number of neutrons by 1. And so essentially what's happening here is that a neutron is converted to a proton. That occurs in beta decay. What about a positron? A positron is like the antithesis or the opposite of a beta particle. So if we have a positron decay, like say for example we have carbon 11, which undergoes positron decay to give us boron 11 plus the positron. Well, we're going from carbon to boron here, so now we're decreasing the atomic number, right? We're going from carbon down to boron, whereas in the first example, the beta decay, we were going up in the number of protons. So here, the number of protons is dropping by 1, and the number of neutrons is increasing by 1. So essentially what's happening here is that a proton is converted to a neutron. Okay? And so when we have beta decay, the ratio of neutrons to protons decreases. And when we have positron decay, the ratio of neutrons to protons increases. All right. Don't believe me? We could do a little math on that to prove it. If you look at the ratio of neutrons to protons for potassium 40, let's say, you have 2.105. If you have calcium 40, then you have 2.000, right? If you look at positron decay of potassium 38, the ratio of neutrons to protons is 2. Then when it undergoes positron decay to form argon 38, you end up with a ratio of neutrons to protons as being 2.111. Okay, so here we see a decrease, here we see an increase. There's another one that's not that you need to know with respect to an electron, right? We talked about an electron. We can represent that as beta, so like a beta particle, or we can use E to represent an electron. Well, again, an electron, we assume it's got no mass and it has a charge of -1. So if an atom captures an electron, and if you're like, how does it capture an electron? The atom basically absorbs an electron from an inner shell, which I'm not going to go into all the details on that. But when electron capture occurs, we have a proton being converted into a neutron, don't we? And so the atomic number is going to decrease. We have a proton converted to neutron, right? Here we have 26 protons. Then it captures an inner electron, and we end up converting one of those protons into a neutron, and we end up with a lower atomic number. So here we're converting iron 55 into manganese 55. All right, and then the last one that involves particles is alpha decay. We've looked at alpha decay already. Here's the example of polonium-212 undergoing alpha decay to produce lead-208. Notice that electron capture decay has the same effect. Okay? It has the same effect as positron decay. Kind of running out of space here. But it has the exact same effect, and that a proton is being converted into a neutron that we saw here. So again, the number of neutrons to protons increases. All right, there we go. So with all that in mind, if we look at the band of stability and we look outside of the band of stability, what kind of decay are the unstable nuclides going to undergo in order to move closer to the band of stability? Well, if you're on the top side or the high side of the band of stability, what's going to happen in that case? The ratio of neutrons to protons is too large in this case, and so those nuclides are going to undergo beta decay. If you're on the lower side of the band of stability, if you're on this side, then the ratio of neutrons to protons is too small, and so the nuclides are going to undergo positron decay or electron capture to get closer to the band of stability. Last one is types of radioactive decay is gamma emission, which is just when a nuclide goes from an excited state to a lower state or a ground state, and it emits a quantum of electromagnetic radiation in the form of a gamma ray. How do we represent the excited state? We represent it with just with an asterisk like that. So if we have an excited state of cobalt, it can emit a gamma ray, and this is the best I could do for a gamma symbol. Okay, so this is supposed to represent a gamma ray being given off here. It's got no mass and no charge because it's simply a form of electromagnetic radiation. We're running out of time here. I didn't get as much done as I wanted to, but we got plenty of time on Friday and Monday. And this is just a summary of the different types of decay and electron capture that we looked at. And so everything that we just covered is basically summarized in this figure. And we'll move on from here on Friday.